Now let's look at regression as curve fitting with minimum error. Plotted here is the training data, the XY pairs, X1, Y1, X2, Y2, all the way up to XN, YN. The goal of regression is to choose from a pre-specified collection FR of simple functions. For example, FR might equal all affine functions. Those are functions with straight line graphs, or all quadratic functions, or something more sophisticated. Find the function that matches the data pairs with minimum error. Now, for a given function from the function class, the mismatch or the error at each data point is simply the function's value at xi minus the corresponding value yi. Let's try an affine function fit to this data. There's a straight line that approximately fits the data, and let's mark some of those errors. Remember that the errors are the difference between the function's value and the actual data point's y value. There's an error, there's an error, there's an error, there's an error, and there's another error. What about a quadratic fit to this data? There's a quadratic fit. Let's mark some of its errors. The errors again are the difference between the data point and the function. They're in green. There's one over here on the right, another one, another one. Let's compare for some of the errors that we marked for the affine function. There's a smaller error, there's a smaller error, and there's a smaller error. So in this slide, some training data has been fit with a affine function and with a quadratic function, and the fitting error at each training point has been defined. Here's a summary of what we looked at visually. For any choice of approximating function, the error at a point is simply the function's value at the point minus the data's value at the point. There's several ways to quantify the amount of mismatch over the entire data set. You can square all the errors and add them up and take a square root. Just add up the absolute values of the errors, or perhaps just look at the maximum error. Treating the EIs as components of a vector E, all of these measures have the properties of norms. Namely, this quantified amount of mismatch is always greater than or equal to 0. It's equal to 0 if and only if the mismatch at every point is exactly 0. And it scales. If the mismatch at each point is scaled by a factor, then this measure scales by the same factor. So the largeness of these all points to some sort of bad mismatch, and the smallness of these quantities points to a good agreement between the data and the fitting function. Now, the appropriateness or correctness of one of these criterion over another really depends on the application. It's not easy to determine that one is specifically better than another. It really requires testing and assessment and is problem specific. We won't go into any more detail here. We'll pick one and work with it for this module. It turns out in some upcoming modules, we'll be able to address the other two criterion as well. So in this module, we'll use the squared criterion, motivated for a few reasons. First, it will lead to least squares problems, to which we've already been exposed in the previous module. That'll be useful. The second thing is that under certain assumptions, it really is the best or the correct choice. Let me give you a little flavor of what I mean by this. Let FR be the class of functions that we're doing our search over. Suppose that the data is generated by a function ftrue from this class, but the data has been corrupted with additive errors. So what I mean is that the xy pairs are related by a function from this class, but there's an additive error a to I in each data point. Now, suppose that these additive errors are independent, random, zero mean, identically distributed with Gaussian distributions. That's a lot of stuff that we're going to actually talk about in the probability and statistics module. Here we're just trying to give an intuitive idea. These are numbers like that obtained with the rand_n function. Under this scenario that this is exactly how the data has been produced from a function that is in your function class, but with independent, additive, zero mean, Gaussian distributed errors, then minimizing the squared error criterion is equivalent to maximizing the probability of having observed the yi's given the xi's. The summary here is that under certain probabilistic assumptions having to do with Gaussian distributions, which we'll learn about later on additive errors, this is the appropriate error criterion to use. That's not to say it's always the appropriate error criterion, because this situation isn't always true. So in the linear programming module, we'll see how to optimize the approximating function choice based on the two other criteria, the maximum error and the sum of the absolute value of the errors.